Hello and welcome to this video where we are going to discuss Standard 10 ICSE Board's Physics chapter Current Electricity. This chapter is very important in terms of your board examination because this chapter will contain from 12 to 15 marks in your board examination. So this is a very high weightage chapter. More so, this chapter is also very interesting. So let's just dive in. Just before going in, let's just discuss that what are the things we are going to discuss in this chapter. Firstly, this video particularly, this is the introductory video of this chapter, and we will further come with a unit 2 and a unit 3 and so on as required according to your book of conscience physics. All right. This video is specifically made for ICSE students, but I am sure this videos would be enough for other boards of class 10 studying current electricity. Alright, just let's go to and just check out what are we going to learn today. And firstly, we are going to study about electric charge. That's the fundamental thing we need to study before go diving into electric current, which is the chapter all about. And after that, we are going to study electric potential. Let me just change the color. So first electric charge, then electric current. Then we are going to discuss about electric potential. Electric potential is something that is going to start study for the first time here, but it is a new physical quantity that is a prerequisite or that is an must for having electric current. So we're going to study that, and then finally we are going to come down to Ohm's law, which is a fundamental and very important law for this chapter, and this chapter will be further governed by this law when we study about series and parallel combinations and EMFs and terminal voltage and whatnot in unit 2 and unit 3. Then we are going to study about resistance, which is a property of a conductor while the flow of electric current. And finally, we are also going to see a couple of small numericals which will be inspired by the previous year questions from your ICSE papers. So this is how the flow is going to be. And now just let's dive in. Okay, so at the very first, before jumping in what electric current is, we need to understand what electric charge is, because this is the fundamental concept behind electric current. Electric charge, okay. So electric charge, if we generally ask the question, the answer comes out to be a positive or a negative charge, or maybe something like electron and proton. But what fundamentally is electric charge? Fundamentally, electric charge is a fundamental property of matter. Property of matter. Now we already know what matter is, right? Matter is anything that occupies space. Space, that means that occupies volume, that has volume, and also has a very important component that is called mass. Mass is fundamentally the fundamental component of matter. So if we define mass, we also define it like it is a fundamental property of matter. So matter is something that has space and has mass, and matter fundamentally is defined by mass. Anything that is called matter would have mass, right? So mass is a fundamental quantity. Similarly, in a very similar fashion, charge, we say charge here is same, a fundamental property of matter, but this is, apart from being fundamental, it is a special property, special fundamental property, where every or all matters are not charges. Like all matters have mass, but all matters are not charges. What's special in this? So charges which are matter have a special property of attraction or repulsion between them or among them. So it experiences a force. We can understand this. We experiences a force internally among themselves. If there are two particles, let's say we understand this with an example. Let's go. Assume that there are two particles. Let's say there's particle number 1, P1, and there is particle number 2, P2. We know that these two particles are separated by, let's say, a distance of d. Now, we also know from the previous classes that gravity would affect because masses are into play. But let's, for a time moment, for a brief moment, let's assume this is just a general assumption to understand this concept. Let's assume here that gravity is not into play. So, no gravity. Okay. No gravity. This is an assumption. Just gravity will be in play, but just an assumption. Let's say there is no external force, no gravity, no external force. Let me also mention this. No external force. No external force here. So if there is no external force, no gravity, and even after that we see that P1 is been pulled towards P2, or let me P2 is been pulled, that means both these particles P1 and P2 are getting pulled at each other, or you may experience something different, or these two might go drift away. This might pull away from each other internally without gravity or without any other external force. It internally either pulls inside towards them, or it pulls outside away from each other. Then we say that these P1 and this P2 are matter, but these are special matters, and the special matters will be known as charges. So these are charges. Charges have a special ability that it internally either attracts or repels. Now we go back to our definition that I have already mentioned here, which is a proper definition, that an electric charge is a fundamental property of matter that causes certain particles to experience a force when placed in an electric or magnetic field. You fundamentally don't know what an electric and magnetic field right now is, but we'll learn this so on and so forth. Electric field or magnetic field is a place briefly where the effect of an electric charge or a magnet is generally felt. So for a brief moment, now you just need to understand that electric charge is a fundamental property. This is the part, fundamental property of matter that causes particles to experience a force. So internally the particles experience a force. This force is either attractive in nature, or repulsive in nature. This is what electric charge is. Now just let's go down and understand in detail what are the next steps here. Let's discuss the formulas for charges. So charges are defined or denoted or noted by a denotation of capital Q or small q. Both are valid. Generally, physics notations are case sensitive, but in this case, charge can be denoted by both Q or small q, caps, non-caps, both. So charges are mathematically defined as Q or small q. Let's just jump in and understand this is a new physical quantity. So you would have a SI unit specially mentioned for this. So just now understand what the SI unit of charge is going to be. SI unit of charge for you is just get me the pen. It is going to be Coulomb, Coulomb. It is named after a scientist who gave the Coulomb's law. It is the last name for the scientist. I don't remember the first one. I should. And it is denoted by the capital C. So what you need to remember that the charges are denoted by Q or small q or capital, and the SI unit of charge is Coulomb, and the denotation sign is capital C. Now, the next step here is to understand that charges are scalar or vector quantities. I am sure you are familiar with what is scalar and vector. So fundamentally, charges are scalar quantities. Scalar quantities. That means that this has only magnitude, and it does not have direction. So no direction, only magnitude. So you need to remember the charges are a scalar quantity. It is denoted by a symbol Q, and it has an SI unit named after a scientist, which is Coulomb, what we can pronounce it as well. All right. Now just dive into some of the mathematical formulations here. Just before the mathematical formulations, I am here going to discuss something very fundamental and important. So just pay attention in this part, okay? This is, I am going to discuss here is very important. I am going to discuss here about fundamental charge. Fundamental charge. Fundamental charge. What is this? Fundamental charge. It is also known as elementary charge. Elementary charge. Alright. Elementary charge. Just look at it right now. What is fundamental charge or elementary charge for that matter? So the smallest charge that is possible, let's say the smallest charge that is possible, smallest charge that is, or that is, or let's say that can exist independently, exist independently, independently is charge on an electron. So the smallest charge that can exist independently in a space is known as the charge on an electron. And we have a fundamental value that is experimentally discovered. So charge on an electron, charge on an electron, is 1.6 into 10 to the power minus 19 coulomb. This is something we already know, but it is very important to remember. This is a fundamental thing of this chapter. What is the fundamental charge? It is the smallest charge that is possible or that is existable in this universe, and that is have a fundamental value that is experimentally taken out. And you just got to remember this because it's 1.6 into 10 to the power minus 19 coulomb. Okay, I hope I'm clear. This is also known as the elementary charge. So if anybody have a question about what elementary charge, it is same as the fundamental charge, and it is 1.6 into 10 to the power minus 19 coulomb, which is the charge on an electron. So the smallest charge possible here is the charge on an electron. Okay, now we'll go down to the mathematical formulations for charge. Now let's go down. See, here we are going to discuss that charge, or let's add something here. Let's say total charge is equals to charge on an electron, charge on one electron multiplied by number of electrons. So what does this mean is, let's say we write down the mathematical formula like this: Q, which is total charge. Charge on an electron is E, and we multiply this with N. This is a famous formula, the first formula of this chapter, which you got to remember. Q is equals to N times E, where Q is known as the total charge, where here Q, just a second, here Q is the total charge that is shown, total charge, right? N here is the number of electrons, because electron is the fundamental charge. So this is the fundamental charge, and fundamental charge we already know is charge on one electron. So charge on one electron is equals to 1.9 into 10 to the power minus 16 coulomb. So this is how this is gonna be. All right, this is the first formula, which is very important for you to remember in terms of making the next part of the chapter. All right. Before moving on, I think we just need to quickly solve a numerical. Let's go and solve a numerical here. Okay, let's go to this part, numerical, which is inspired by a previous year question. And here we have a question. Okay, this question requires you to know a few more bits of things. So let's go back here. You just need to cut this part maybe. Okay, we cut that. Okay, this is what you got to remember. And now we are going to discuss the properties of charges. So next up is properties of charges. Very important, very easy. All right. The first property coming up to you is right here. It says attraction and repulsion. Like charges repel each other, while unlike charges attract each other. So the first property says that if you have a positive and a positive charge, which is like charges. So if you have positive charge, or let's say we have a negative charge, these are going to repel. These are going to go away from each other. While on the other hand, if you have a positive negative charge, or let's say a negative positive charge interchange, this is called unlike charge. This is called unlike charge. This says that this is going to have an attractive nature. Attractive nature. I hope I'm clear. So you can see here, like charges repel each other, while unlike charges, you know, by unlike charges attract each other according to the Coulomb's law. You don't know the Coulomb's law, but we're going to study that in the years to come in your 11th and 12th standard specifically. Okay. Now, this was our first property to say. Now, moving on to the second property. The second property here says quantization. This is an important property. It says electric charge exist in discrete packets as well as integral multiple of the elementary charge. So we need to understand this. Property number 2 has to be explained. So quantization of charge. Quantization of charge. So what is quantization of charge here? Quantization of charge, it says that all the charges either exist or gets transformed in packets. Let's say there are multiple charges and all the charges would be in a packet. Let's say this is packet number 1, P1. So it will have charges electrons, 2 electrons, then maybe have 5 electron and 1 electron. This is a packet and this is going to move together. So you can have another packet. It does not exist independently. It exists in packets. This is what they are saying. So it will be a group of electrons, a group of protons, or group of any other charge. This may be a P2 and this will have another set of electrons in it, and this is how this is going to be. These are known as discrete packets. These packets will be discrete and individual packets, and you can be able to identify them. These would be packets. Right. There is more information to the quantization of charge. The quantization of charge also says that the charges would be an integral multiple of the fundamental charge. Now, this is very important to understand. What does this say? This say just note this down, that what does this say? This, let's just check it out. This says that integral charge will be always be integral multiple of the elementary charge. Now, integral multiple of the elementary charge is the smallest charge, and that is equals to E. 1E, let's say, or E, and we know what is this. This is 1.6 into 10 to the power minus 19 coulomb. And what does this say? This is the very basic charge that exists in this universe, and the next charges would be more than this. And if it is more than this, it would be integral multiple of integers. Multiple of integers. I break this down for you. Integers. I break this down for you in the sense, let's say charges would exist like 1 electron, 2 electron, 5 electron, 6 electron, 10 electron, and so on. This is the correct way of representation. But charges won't exist. Charges won't exist in the form of decimals like 0.5 electron. This is not acceptable. Let's say 4 by 3 electron. Let's say minus 1 by 2 electron. This is not acceptable. The red mark here is not acceptable. The charges cannot exist in this form. Charges only can exist in integers form. So no decimals and no decimals and no fractions allowed. So this is the part here. So this is a fundamental. Only and only it can be integers. Only integers are allowed. No decimals and no fractions would be allowed for the charges. So the smallest charge will be E, and then 2E, 3E, 4E, 5E, and so on. Okay, so this is all formed. Okay, let's move on and let's say what all other properties we have. The next property is additive property. This is a very fundamental property. Additive property, just let's say we discuss it here. The additive property just says that we can add charges algebraically, just like we add algebra. Like q will be an addition of small charges q1, q2 and q3. So this is a scalar quantity. Algebraic addition is possible. Algebraic addition addition is possible here. Just like you add in maths, we can add charges. We do not have to worry about directions and all. Is possible here. Possible because because charge because charges are scalar in nature. Are scalar. If it would have been vector, we could not have done this algebraically. Then we have to have it vectorly. But this is addition of the simplest order. This algebraic addition, and you know it very well. And we can add it. Now, next is conservation of charge, and this is something you already know. Charges can either be created nor be destroyed, and it can only be transformed from one form to another. And then this is what the both discuss. Transferability of charges is basically by 3 points. We can transfer charges by generally 3 types, but there may more and more ways. But the 3 famous ones are induction, then we have conduction. Fundamentally we should have conduction before, but it's okay. And then the third one would be rubbing by friction or any other rubbing. So this is something that is not so important. The first 3 points are very important. The last 3 is not that important because it is of the electrostatic nature. But we are here studying electrostatics. No, we are studying electricity. That's a part of electrodynamics. So in this case, that is not very much of importance, but yeah, you should know this. This is something we have already studied in the previous classes, how there is transfer of charge. The next part, we are now entering in the world of electric current. Okay, now let's dive into the next topic, which is electric current, and this is all about the chapter electric current. This is generally defined or denoted. Firstly, we need to know the denotation sign. The denotation sign is small I or capital I. Both works in this case, caps or non-caps. So it is denoted by I. Firstly, before understanding it, let's define it properly. Electric current is defined as the rate of flow of charge. Rate of flow of charge with respect to time. All right. Let's first understand what actually is electric current. Let's take 2 examples and analyze them bit by bit. Follow me. Let's say we have a case number 1. This is case 1. And I'm saying in case 1, let's say we have a negative charge Q placed at a point A. All right, let's say the negative charge Q might be some electron or anything, but presently we just say it's a minus Q charge and it's placed in position A. The other information about this case 1 is the location of this location. If we discuss the location, here is A. Okay. The charge here is negative. All right. And the third point here is the charge here is at rest. So the velocity, just a second, this arrow mark, the velocity here is 0. So velocity is 0, that means it is at rest. So the charge is at velocity 0, no speed. So this charge is presently at rest position. Okay, now if we move on to case number 2, right? If we move on to case number two here it is case two. Let me describe this. Let's say we have the same charge, minus q, same charge, and it's now at A position. But I change something. I change what we can do is we can say that the charge is now moving with certain velocity v. So it is not at rest anymore. So the points here would be that it's moving from, let's say, A to a point, new point B. So this charge is going to move here, right? It's presently moving with a velocity or a speed of v for now. Let's say the present location is unknown, and in this case, location, we are going to say the location is from A to B. So it's in between A and it's going to B. Okay. The next point, it is same negative charge. Okay. And for this second case, we define that the velocity in this case is not zero, it's a non-zero velocity. This means that this charge is in motion. Now, both are at your screen, case 1 and case 2. See, in case 1, this is a negative charge and it is at rest. The same negative charge in case 2 is now moving with certain velocity v. Now, the thing here to understand is the location here is A. So the position is not changing. When the position is not changing, we can say this is at rest, right? So this position, case 1, is known as an electrostatic case, where the charge is static. So this here, we can mention it, that this here, case 1, is a static case, which is called an electrostatic case. Means this case, the charge it at rest position, and this is an example of an electrostatic behavior of the charge, where the charge stays where it is. But in case 2, here comes the case 2 part. Case 2 is not electrostatic, it's electrokinetic or electrodynamic. Kinetic form. The charge in this case is moving with some certain speed, certain velocity towards B. So there is change of position. Change of position. What change of position of the charge? So whenever there is a change of position, or in just we can say whenever there is motion, whenever a charge is moving, the moving charge, the phenomena of the moving charge is basically known as the electric current. This is basically what we know as electric current. Electric current is nothing but a movement of charge. In very simple terms, we can generally understand that electric current is basically movement of charge. If a charge moves, let's say the charge is positive or negative, it does not matter. If the charge is moving, that means this charge is in electricity form, that is called the electric current. So whenever a charge is in kinetic form, that is the case number 2, when it's moving. So moving charge is basically what we define as electric current. I hope I am clear. Now we can go on to the details. The definition here was the rate of flow of charge. I'll just correct this part. Pardon me for my handwriting. Just give me a minute. I'll just write the flow once again. Okay, this is FLOW, rate of flow of charge with respect to time. Now we'll discuss this in context of how it is defined in your books. Let's say there is a point A and we had a charge Q. The charge Q can be positive or negative, and if it is moving towards, let's say, a point B, and the charge will somehow at some point would reach charge B, and at point B it would, let's say, reach after some time. So movement would take some time, let's say T. So electric current is defined as, mathematically we can say, mathematically we can define electric current can be defined is equals to total charge flown divided by total time to flow. this is what how the mathematical formula looks like. We'll write it in terms of notations. So electric current is defined as I notation wise. Total charge will be defined as delta Q, that is change in charge, and divided by delta T, that will be change in time. So this can be defined as change in charge, change in charge. Change in charge is calculated to find out what is the total charge flown, and this is the change in time. Change in time. Right. So this is notation. If there, you can on for simplification, we generally just write I is equals to Q by T, or this can be written as small q by T as well. So this is what the general notations of electric current is going to be, and you need to know this fundamental. Now there is one more part to this. Just give me a second. I mentioned that too here. Uh, we have studied about charge, and we already know, right? We know here that Q is equals to N times E, where N is integer and known as the number of electrons. So if electric current can be defined as a part of flow of electrons, but we can also remember that flow of electrons is not electric current. Flow of any charge is electric current. But basically, in classical theory, we just say that electrons are free to move and protons are inside the nucleus. So we generally define it as electrons move, but we generally don't know what moves. We just know the charge moves, and we can write or define electric current as Q upon T, and the Q can be written as N times E upon T. So we can have a final formula that I is also equals to N E by T, where N is the number of electrons and E here is charge on one electron. This is the fundamental charge or elementary charge on one electron in this way. Okay, so this is how it is defined. Now, moving on, electric current is a fundamental physical quantity, so obviously you need to study about the SI unit of it. So just quickly study about the SI unit of current, that is I. So I is defined as Q upon T. Q is Coulomb, right? And T is second in SI. So we can write current can be written as C, just a second, COLOUMB, Coulomb per second, or this can also be written in the form of C by S, or can be written CS minus 1. Right, both these forms must be familiar to you. This is an exponential form, and this is called the exponential form, and this is called the fraction form. Okay, moving on, we will just mention a few things. That 1 coulomb per second is defined by a new unit, and that is called 1 ampere. AMPERE, and it is denoted by capital A. And the interesting fact in this matter is this part here. This part here is what we define. Let me draw this straight. This is the SI unit for electric current. SI unit of electric current. So if we need to define what is the SI unit, it's ampere. The fundamental unit, this is the SI unit, and this part here would be described as the fundamental unit. Fundamental unit. Both are the units, both are correct units, but for instance, what is called the SI unit, so you need to call out its ampere. SI unit of current would be ampere. AMPERE. Very important, and is denoted by a capital A. This is called the SI unit. I hope I am clear. Now, just moving on to the next part where we are going to discuss that electric current, current is a scalar quantity. Scalar quantity. It is generally a confusing topic if you go very deep into this. It is actually a tensor quantity. Tensor quantity, but we have at this level not studied what is tensor quantity. But for you, electric current would be a scalar quantity. That means this would act or behave, add and subtract like other scalar quantities, which only deals with the magnitude. Magnitude. Electric current does have direction, but it does not have a fixed direction. So fixed direction is missing in this case. Therefore, this is can not be called a vector, and therefore it is called a scalar quantity. Okay, now we are going to study potential. The video is quite long enough, so it would be better if I make a separate video for potential. Potential is a very interesting concept, and this is something you are going to learn the first time. You have learned about potential energy. This is somewhat similar in reference to, but this is a new physical quantity. It's a new physical quantity. And if it is a new physical quantity, you need to learn it through and through, because this is something very important, and it is a little confusing because it's highly mathematical and the physical significance is a little dull here. So what we can do is we can make a part B of this video so that it turns out to be a better case where the explanation of the potential is better. So we'll do the rest of the topics, that is potential, then we'll do Ohm's law, then we'll do resistance, which will be resistance, and then after resistance we'll go and discuss the resistivity, which is very very similar to resistance, but it has its nuances. So we're going to discuss these in the next video so that this video does not become long and I get enough of time to explain the main part, which is the potential. And also we are going to solve the numericals there. We could not solve numericals in this, so the next part of the video where we have potential, and then we'll discuss Ohm's law and then solve numericals as well. So see you in the next video. Till then, have a good day. Thank you.